Finding the forces acting on a rotor turning with eccentricity. Article 10.3 of the book Mechanical Systems Calculations of the Marine Facilities. Let's consider the exercise. So we have the assigned mechanical system. Mechanical system is the electric motor. Electric motor consisting of two parts. The one part is a rotating rotor and this electric motor with the definite eccentricity. Eccentricity we say E, with the center of the mass of rotor is C1, and this is eccentricity. And we have as well the stator. The stator is a part of the mechanical system of the rotating electric motor with the center of the mass C2, center of the mass of stator. And the exercise assigns one to determine the equation of horizontal vibrations of electric motor, assuming not bolted to the smooth foundation. So we have as well the bolt fastening, but if there would not be the bolt, so what is the if we neglect as well the friction force between the electric motor and the smooth surface, what will be the equation of horizontal vibrations of electric motor, assuming not bolted to the smooth foundation? This is first assignment. The second one is the time pattern of changes of the horizontal shear force acting on the electric motor mounting bolts. So we have the fasteners here, the mounting bolts, and if they are there, what will be the pattern changes the horizontal shear force sharing the fasteners. And the third is the value of angular velocity of the rotor at which the joint of the electric motor mount opens. Yes, if we assume with not fastening by the bolt, but like just the pin limiting the transverse motion of this definite one mechanical system as electric motor, just a pin, not the bolts here, with not the screw, with not, and what will be the angular velocity? What have to be the angular velocity if the joint of the electric motor to this definite one surface, smooth surface, will open. So when the force of the inertia in the extremal position of rotor will be more than the forces of the weight of the rotor and the stator together. So first, we can begin that the equality of zero displacement of turners of the mass of the mechanical system, x C0 and x 10, and the stator x20, the rotor into R. So we had this like the original, assume that the abscissas of the center of the mechanical system, the common center of the mass and the center of the mass of rotor and stator is zero, time equal to zero. The mass of mechanical system, I mean the electric motor, equals mass of the rotor and the stator, equality to zero of the impact of mechanical system. So we have no external forces, only the forces on behalf of the elements of mechanical system. And rotating rotor is a cause of the any forces acting in the mechanical system. Yeah, exactly. Besides with the external forces of wedge and the support reaction, I mean, in the projection of this x equality to zero of the inertial forces and moments. So if we do not have the transverse forces applied to the electric motor elements in the projection of the abscissa, so we have the theorem of the motion of the center of the mass equal, that is the mass of the mechanical system, including the rotor and the stator, multiplied by the acceleration, horizontal acceleration of the center of the mass of mechanical system has to be equal to zero, because it only if we have no zero mass total of the mechanical system, that is the zero is the acceleration, horizontal acceleration of the mechanical system with not action of the external forces. That is y is. If the center of mass is stationary, that is the abscissa of location of the center of the mass mechanical system is constant, definite constant. So the equality to zero static moment of mass of the system. Static moment have to be equal to zero. And what is static moment? If we assume, after this, all assume that it not moves originally we have no external forces applied to the mechanical system, then the static moment, the mass of mechanical system multiplied by the abscissa of its center of the mass of the mechanical system equal to mass of the rotor by the abscissa of the center of the mass of rotor, and plus the mass of the stator and the abscissa of the center of mass of stator. The location of the center mass of the mechanical system when rotating with eccentricity. So we assume as well that we have definite eccentricity, because this is eccentricity, this the distance between the axis of the stator and the axis of the rotor. We have definite eccentricity, like just a definite segment. Yes, this could be due to the technological reasons or due to the other reasons that it could be the definite eccentricity. It's not 100% balanced mechanical system, but it rotates with the eccentricity. And the location of the point of the center mass of rotor is minus eccentricity plus sine phi minus x2. Eccentricity multiplied by the sine of the angle of the inclination plus x2. So we have definite angle of the inclination. And the x1 equal to x1 equal to this eccentricity. Eccentricity is right angle triangle. If we will multiply eccentricity by the sine of the angle of the inclination when rotating this rotor relative to definite one point, the point exactly could be the center of the mass of the mechanical system anywhere within inside the segment of centers of the masses of the rotor and the stator rotor and so on. And what is the abscissa location of the center? If we are coincide the ordinate axis passing through the center of the mechanical system mass, then x1 equal to the eccentricity. This is a hypotenuse of right angle triangle multiplied by the sine of phi angle, that is this one leg together, x1 and x2, and x1 equal that eccentricity multiplied sine phi minus x2. This is well understandable. And the dependence of the system static moment of mass on the eccentricity on abscissas of the centers of mass of the rotor and the stator we can find here if we will substitute here the in the equality to zero of the moment in the equation for the static moment of the, we characterized the location of the constant location of the mass center with no action of the external forces. The constant static moment when the product of the mass of mechanical system by the center of the mass of the mechanical system, we substitute here this equation due to as for the abscissa of center of mass of rotor here instead of we can find this definite one question. This have to be equal to 0. The abscissa of center of the mass of stator when rotor turning with eccentricity, with a definite one eccentricity, is not, we don't know why the eccentricity, but it is usually, assuming the constancy of the aerostatic moment of mechanical system is. So this is the first decision, that is, we can find here, what we can find here? We can find here the abscissa of the center mass of stator. From this equation, if it's equal to 0, we can find that x2 equal to this one, summand, this one. Just we can move it to the right one with the change of the sign and considering the mass of stator 2. This is a mass of rotor and the stator. And we can find next we can find next yes m here again with that we discover for the brackets exactly. And next we can find that the pattern of the of x2, the if we have no friction and just if we have no bolt, no friction, no fastening to the surface, and no friction, and when the rotor rotates using the theorem of the center of the mass motion, considering that all, we can find that the pattern of the moving of one element of the mechanical system, that is the stator, dependence on time, the pattern will be like this definite one form. The eccentricity, the mass of mechanical system, mass of rotor, the sine omega by t. This is the omega by t angular velocity of rotation of rotor, and this is the angle phi omega by t. So next question, we have to decide the time pattern of changes of the horizontal shear force action on the electric motor mounting bolts. The first one we did decide, we got it. We got it. So the next is what is the force Rx? Rx, the force, horizontal force acting on the bolts, on all bolts together. Just generalize it. Index of the shearing force, the static moment of the mass of electric motor when the starter is fixed to the by the bolts to the surface, and x have to be equal to 0. Is is about the same approach, but perhaps it's more comfortable to coincide the beginning of the system, or the reference of the coordinate system x with a point of the center of the mass of the starter. It's about the same, but to do that, assume of the location of the system. It little will simplify the equations. We can did as well with considering the reference point here, and due to make the ordinate axis passing by the center, common center of the mass of this mechanical system of the electric motor, but more comfortable to take it here. I mean the center of the reference of the coordinate system, because some summands in the equations will be equal to 0 in the different one case. So the static moment of mass in the new one taken considering the coordinate system when starter is fixed and the x2 equal to 0 is that the static moment characteristic of the motion center mass of mechanical system, the abscissa of center mass of mechanical system, this equal of the mass of rotor. We consider that when we fasten by the bolts the starter to the surface, now we have zero displacement, of the starter, of the starter relative the support surface. This is and in this case we have the horizontal force, external force action on this mechanical system, and it is equal the external force for the product of the mechanical system by the acceleration projection on opposite axis of the motion of center mass of the mechanical system as due to the rotor rotates the center of the mass of rotor. Then the center mass of mechanical system C, which is in between the center mass of stator and the center mass of rotor, will rotate the center mass of mechanical system. Electric motor will rotate to. Then the force will be equal to the just only one summand remains here, and this force will be equal the force equal to this one, definite one. The static moment of the mass of the mechanical system total, this force will be equal. Oh, excuse me. This force equal to the acceleration of the center mass of the mechanical system, and will be equal to the remain summand with a minus, and because of those directions of the force applied to horizontal force in the bolt, the shearing force. And the magnitude, looking here, we can find that it is exactly understandable and obvious that when rotating, it is the horizontal force will be of the trigonometric form, like could be sines form. Sines, it depends exactly on the initial condition, but not so much important. We have to find the maximal magnitude. And these first three factors together are the maximal magnitude, the maximal amplitude of the horizontal component of internal force, inertial force, is the shearing force as well, because it is the forces of inertia when rotating the rotor, is equal to the product mass of rotor by the eccentricity and multiplied by the squared angular velocity of the electric motor rotor rotating. This is answer for the second question. The second question, we had the time pattern of changes horizontal shear force acting on the electric motor mount bolt. That time pattern is like a trigonometric function, like the sine shape dependence of the horizontal shear force and the amplitude of this. We have the frequency of this sign is of this pattern. Frequency is the frequency of the rotating of the rotor, and maximal magnitude we got as the eccentricity multiplied by the mass of the rotor and multiplied by squared angular velocity that is characteristic for the normal acceleration. And next I show we have to find the value of angular velocity of the rotor at which the joint of the electric motor mount opens. Assume that we have no bolt here, but we have just a pin. Limiting the transverse motions could be, but in the mechanical system, the electric motor, the stator and the rotating rotor keeps on the place only by the action of the forces of the wedge, and when the inertial forces of the mechanical system move, and that is the mass of the mechanical system total together with rotor and stator moves, and the action of the acceleration of the center of the mass exactly here can we have vertical component in the projections on the ordinate axis. So this is about the same decision as in the previous one task. As well, we will have the coordinate system with the adopting the reference point with the stator. It's more convenient because we have less of the summands in the equation final we have. And only we will consider the projection of the accelerations and the motions on the ordinate axis, not on the abscissa axis we did before, but on the ordinate one. Okay, so this was finding of the maximal shearing force. The amplitude of the force inertia is equal. This is amplitude of the force of the inertia in upper phase position of the turn. We can do the same. Find all the projections on the axis of the ordinate. This got for the instead of x we can substitute just a y. Y is a variable by the another one coordinate axis, vertical one. But we can assume that we did all that, and considering the amplitude of the vertical component of the inertial force, we have the same. And this vertical component of inertial force have to be equal to the weight of the mechanical system together, gravity acceleration, mass of rotor, mass of stator. And considering that, we have to find the angular velocity at which the force of inertia, the maximal magnitude of which is when the rotor is in the upper one position. And this position, we will have the angular velocity at which the inertial force exceeds the force of the wedge. So this is not be difficult, and we can find the angular velocity. We have to decide it in the show the value of angular velocity of the rotor at which the joint of the electric motor mount up. If we have not the bolts here, but the pin and the keeping on the place only on the action of the wedge, this it will be the gap will be open here between this mechanical system and the surface, a definite angular velocity of rotation, because in the upper position we have the upper position, you know, when eccentricity is to the upward direction. In upper position, we will have the definite the force of the inertia considering the normal acceleration when rotating with the eccentricity, and the angular velocity determined by this definite one equation, the inertial force will exceed the force of the weight of the mechanical system. In this case, the gap will open between this mechanical system and the surface of its location, if not bolted, but just only located with like the pins, no limiting the vertical displacement of the mechanical system, only the horizontal one. So questions and comments. Eccentricity of rotating elements mechanical system, which causes cyclic motions or other element of the system and the cyclic reactions acting on the fixed supports. The fact is that in any case, the quality of the construction of the mechanical system rotating, in particular the electric motors, could be the perfect 400%. In any case, we have some eccentricity, and when the rotating parts rotates with eccentricity, because that is when the axis of the rotation not coincides with the point of the center of the wedge of the rotating parts. This can cause the oscillations of the forces and the motions. If we have limited motions, we will have the oscillated forces acting on the fasteners. If we have no the fasteners, we will have the oscillations of the mechanical system. 10.3.2 critical elements of motion of rotating elements of mechanical system in which directions of the supports have limiting values and disconnections are possible of open supports in which the mechanical system is held by wedge oppression forces. Yes, if we do not have the bolted fastening, so then the mechanical system is on the support only by the action of the wedge. And if the forces of inertia due to the normal acceleration acting on the rotating parts of the mechanical system will exceed the total weight of the mechanical system, then it is possible the opening of the gaps between the supporting surface and any kind of the fundaments and the mechanical system. 10.3.3 finding the displacements of the stator not fixed on horizontal surface when the rotor turns with eccentricity. Determining considering the constancy of static moment of rotor and stator total mass, which are not affected by external forces, as a result of which the total acceleration in the plane of the supporting surface is zero, and the velocity of the common center of mass is equal to the initial velocity, also zero. And the movement of the common center of mass does not occur. If we neglect the friction forces and if we consider the rotating element within mechanical system, and if we consider that the mechanical system is on the surface, on the smooth surface with no friction, then we will expect the oscillations in the motions of the mechanical system with the rotating elements with definite frequency of the rotating of this element. So this is due to the oscillations of the common center of mass with the definite. And it could be the horizontal translational motion, that is these circumstances we told about is on the horizontal motion with no action of the external forces, like the forces of weight. In the horizontal plane, we do not have any forces. If that, then if the system possesses the initial velocity horizontal, it can keep the motion translationally with a definite initial velocity, with the oscillations due to the rotation of the element mechanical system. And if it do not has, the mechanical system, the initial horizontal velocity, then it will has only the oscillations in the horizontal direction along the smooth surface. And if we neglect the friction of the surface, we usually can neglect because the forces as the forces of the inertia when rotating the mechanical systems elements could exceed in the great degree of the friction forces, which can be practically available, but we assume they are not, as forces of inertia exceeds these friction forces in the great degree. 10.3.4 determination of reaction of the support when the stator is secured, preventing the horizontal movements considering the angular velocity of the rotor in mass and the eccentricity. If the support is secured, then this means that we have the external forces acting on the mechanical system. The action of the mechanical system as a secure of the support caused that when we consider the the motion of the center mass of the mechanical system with the rotating element. It have the stationary element and rotating one element, and in this case we have definite common point of the location of the center of the mass of the mechanical system consisting of these two elements. And if the system is secured as well, we have the force in the projection of the horizontal axis or in vertical axis, which is in the equation of action on the mechanical system, that we can find this force required to limit to the motion in any direction of the mechanical system, considering the theorem of the motion of the center mass of the mechanical system. The center mass of the mechanical system anyway will be, because at least due to the availability of the rotating part with the eccentricity, rotating part of the mechanical system with the eccentricity. But the stationary part mechanical system will not move, and in this case we have to include the external force in the equation, and we can define this external force which required to constrain the availability of the displacements in the horizontal or in the vertical directions in any case. 10.3.5 opening of joint supporting a loose motor on the horizontal surface, which occurs when they are passing the upper semicircle of the trajectory of the center mass of a rotor turning with eccentricity. In projection of the centrifugal force exceeds the if projection of centrifugal force exceeds the total weight of the mechanical system, the rotor, stator, or motor. Yeah, exactly. We can find the centrifugal force as the eccentricity multiplied by the squared angular velocity multiplied by the mass of the rotating part. And if this mass of or multiplied by squared angular velocity and multiplied eccentricity, that is multiplied by the normal acceleration of the rotating part, if this exceeds the weight of the mechanical system total with rotating and the stator parts, the gap between this mechanical system and the surface on which it is installed, the gap will open if we have no fasteners. If we have fasteners, like the bolts, we can determine the force acting on these fasteners as a difference between the force of the inertia and upper, I mean the magnitude of the force, the amplitude of the force in when the rotating part passing the upper semicircle. For example, for the mechanical system installed on the surface, we can find the amplitude of the force acting into the fasteners as the force of inertia subtracting the total weight of the mechanical system. Thank you.